Welcome to the Sci-Fi Guest Show. I'm your host Jack, and in each episode I'll be talking to a different scientist about their research or topics they know best. In this episode we'll be talking about astronomy, the formation of the universe, and galaxy-killing black holes with Professor Romeel Davé. Romeel completed his PhD at the University of California, Santa Cruz before working on projects all over the world, and is now Chair of Physics at the University of Edinburgh. So welcome to the show, and thanks for coming on to do this podcast.
Thank you very much, Jack.
Now, I gave a very brief overview about your work history and the type of research that you're involved in, but could you explain that in a bit more detail?
So I am a numerical cosmologist, which means that I try to understand the origin and evolution of the universe. And particularly, I'm interested in the question of why does the universe look the way it does? And so when we look out in the universe, essentially, the thing that we see that marks out the way we measure the universe is galaxies. The galaxies are of course collections of stars located at millions or sometimes billions of light years away from us, and their stars shine, and we can see that. And we see that galaxies come in an incredible variety of shapes and sizes and colors, and they change over time. And understanding this is sort of like in some sense, the origin story of us, of our own Milky Way. How did we get to be a spiral galaxy here, with our sun living in the outskirts? And so this is the kind of thing that really interests me.
Yeah. And to actually find that out, I know a lot of the work you do requires the use of simulations, but why is it that you have to use simulations to carry out research into the universe?
So essentially, we astronomers have a bit of a problem compared to a lot of other scientists in that, usually you imagine science, the old scientific method where you set up an experiment to test a hypothesis, and then based on the results of that experiment, you revise the hypothesis and so on and so forth. Well, that's all very well and good if you've got a lab where you can set up an experiment and do it. But if you're interested in astronomy, your experiment is, incredibly far away, and we can't certainly get there, nor could we even, do anything. There's no equivalent laboratory in astrophysics. It's an observational science, which means all we can do is collect the light that we see, analyze it, and try to piece it together. But the difficulty with this is, of course, that it's something akin to the blind men and the elephant problem, where each wavelength of light or each piece of information gives you a little bit of the story. But how do you synthesize all of that into one coherent story for how all this happened? And that's where the simulations come in. The simulations are basically trying to model, at least the ones that I do, are trying to model a representative portion of the universe with everything that's in it. The galaxies, the stars, the stuff between galaxies, the clusters, the black holes, all of that goes into these simulations. And in doing so, we hope to effectively set up a laboratory where we can say, okay, what happens if we change this bit of physics over here? How does that affect something that we might be able to see in our telescopes? And so this is the kind of experiments, is effectively a way of doing numerical experiments. We input physics into the simulation. We run the simulation from close to the Big Bang until today. And we look at the simulation and say, how does it compare to the real universe? And in doing so, we continually have to add more and more physical processes so that we can better match what we see out there in the universe. And the hope is that this is moving us towards a better understanding of what is the physics that got us here today.
Yeah, and to carry out the research using simulations, are you looking mostly at the patterns you can see, or do you make changes within that simulation to see what the effect is?
The sort of work I do is often called Endbody simulations. And the idea of an Endbody simulation in principle is very simple. And it is that you say that, okay, I have let's say a chunk of the universe. I'm going to populate this chunk of the universe with a whole bunch of particles, let's say. And each particle is going to represent some portion of the mass of the universe, some small portion. And I can have millions or billions, or these days, some people even get up to trillions of particles. And then I have all the particles set up at an initial time, very close to the Big Bang. And I let those particles interact via forces like gravity, hydrodynamical forces, if those particles happen to be or gas, type particles. And we evolve that whole system forward in little tiny steps. It's sort of exactly what the universe does, except it's much, much coarser. The kind of particles that we're talking about are a single particle represents a mass that is maybe 1,000,000 times the mass of the sun. So we're not going to model individual stars if we want to model a big cosmological, representative cosmological volume. So essentially that's the idea, and that's how you sort of evolve it forward from a very early time until, for the 13 some odd billion billion years of the universe, and get to today.
And could you use a simulation to predict things?
Right. So it depends on what exactly you mean by prediction. So, of course, what you'll notice is that these simulations predict the complete evolution of the universe. Well, not quite complete. We start a little bit after the Big Bang, but nearly the whole history of the universe. So that means that we can look at our simulation at any given time. So we can go to today, let's say, and say, hey, look, there's a galaxy in my simulation that looks something like the Milky Way. What did it look like 1 billion years ago, 10 billion years ago, right? We can see that evolution. And then we can go out with our telescopes. And of course, as we look farther out in space, we're effectively looking further back in time because it's taken some time for that light to travel from the distant object to us, which means that with our most powerful telescopes, things like the Hubble Space Telescope, we can see out to galaxies as early as 13 billion years ago. So by taking various pictures, we can then create essentially snapshots of the universe at various times and understand how it is that essentially our galaxies that we see today looked like in the past. And that's the idea with these simulations, is this allows us to then connect the dots that we can measure in our telescopes.
So in a sense, you can actually see the past. You're not predicting it, really.
Yeah, so you can see it on one hand, and then you can model in the computer on the other. And then again, so we can do that comparison, not just today, but we can do it a few billion years ago. We can do it in the very early universe, so on and so forth. And the idea is if we can faithfully reproduce this galaxy population, then the physics that we've put into the model must be, well, hopefully is something close to correct, right? So it's essentially goes back to this idea of the numerical experiment, where we run a whole bunch of different simulations, turning processes on and off, changing things, and trying to understand what matches best. And if we can do that, then what we can do is we can say, hey, look, I've got 2 different models, let's say, and both those models seem to match everything that we see so far. But we've got this new telescope coming up called the James Webb Space Telescope, let's say. And with the James Webb Space Telescope, we'll be able to see much more detail than we can see even with Hubble Space Telescope. So if we could see with such detail, what new things would we discover? Which of these 2 models that I'm trying to compare between, what did their individual predictions look like? Can we discriminate between whether one model is correct or another model is correct based on this new data that we're going to get? And so it's a way of sort of understanding what is the key questions, what is the key physical questions that we have about galaxy formation, and how do they manifest in observations. So that's one of the uses, for instance, of simulations, is to make predictions for what will be seen with upcoming telescopes and what will be the most effective way to use those telescopes to elucidate the most pressing questions right now in the physics of galaxy evolution.
And what would you say are the most pressing questions right now?
Well, certainly there's a number of them. I think one of the key questions that has come to light by basically, I would say, in the last 10, 15 years, is that if you look at an image of the cosmos taken with Hubble Space Telescope, just go Google Hubble Space Telescope deep field or something like that. You see a big sort of mostly black area with little points of light all over it. And each point of light that you're going to see is going to be a galaxy. So each one is sort of an individual collection of stars located, we don't know how far away just by looking at the image, but we have other ways to figure that out. So you get the impression that galaxies are sort of these, what Immanuel Kant once called eyelid universes, right? They're literally just themselves out there in the middle of space, not really connected to anything else. And I think in the last 10 years and 15 years, essentially simulations have paved the way to completely overturn that idea. The idea is, in fact, that galaxies live within these cosmic ecosystems where material is flowing in from the galaxy, material is flowing out from the galaxy. There's energetic processes that are throwing stuff around. There's supernovae that are going off. There's the black holes in the center of galaxies that are doing some things that we don't fully understand. And this entire cycle that goes on of movement of gas in and out of the galaxy is what the astronomers these days call the baryon cycle. And the baryons is just essentially the astronomer's word for anything in the periodic table, basically. And so it's the movement of this gas in and out. And some of it, of course, forms into the stars that shine, and some of it goes down in the center of the galaxy where there's the black hole. So there's this very complicated dance that goes on. And understanding this dance is I think, one of the key questions. And it encompasses everything from very, very large scales where we're talking about, the gas is coming in from out in very diffuse space, and that, when you look at an image, all that blank black area, it's full of gas, right? And that gas is being drawn into the galaxies slowly, very slowly, because, the distances are enormous here. But eventually it falls in, then all kinds of things happen to it. Some of it gets back out. Some of it goes out very, very far, at least according to some of our models. And so there's this baryon cycle that's, I think, essentially is the way to understand galaxy formation. But how all that works, I think, is pretty uncertain at this point. We don't know what exactly is the way we see material being driven out of galaxies. Why? We know that there's some energy from supernovae. Maybe there's some energy from black holes. Sometimes galaxies seem to be driving out material because of supernovae. Sometimes they seem to have outflows because of black holes. What decides which one is where? When the black holes turn on, it seems that galaxies maybe change from being spiral-like to more elliptical dominated. Why does all this happen? And that whole dance, I think, is the key question in astronomy. And it brings in a huge amount of various topics, including things like chemistry and, the formation of heavy elements like carbon and oxygen, the things that, we need for life. These are all formed, of course, in the insides of stars, blown out by supernovae. Those same supernovae are distributing all this stuff all over the universe. So how does this all work? And I think that is sort of the overarching question. And the idea with these simulations is, of course, that in principle, if we can model everything correctly, the simulation should just naturally produce this, right? And that's, of course, the real challenge here.
So was it surprising that space is filled with all these gases and things? Because I think a lot of people, me included, would think that space is absolutely empty.
Exactly. And so, one of the things that I think comes as a surprise to a lot of people is if you look at let's say, this Hubble Space Telescope image and look at all the points of light, you're looking at about 5 to 10% of the total matter in that region. There's vast majority of it is stuff in between galaxies, the so-called intergalactic medium. That contains far, far more mass. And the problem is, of course, it doesn't shine. And so, it's a lot harder to take a picture of it, but there are ways. There are ways to actually detect this stuff, and we know it's out there.
But you needed to bounce the light back to easily detect it, I guess.
Exactly. And, if we want to see other things, we have to be a little bit more clever, which is fine. Astronomers are clever, but it is more difficult for sure.
Absolutely. So another topic that we discussed before the podcast was galaxy-killing black holes, which I really want to hear some more about that.
Yeah, so the relationship, particularly between black holes and galaxies, I think is one of the really crucial ones and one of the very poorly understood aspects of this whole process. So it is known at this point, I would say, that just based on incredible amounts of evidence, that virtually every galaxy of any size has a supermassive black hole in the middle. And by supermassive, I mean typically at minimum around 1,000,000 times the mass of the sun, going up to tens of billions of times the mass of the sun. So, for instance, if you look in the center of our Milky Way, our black hole is actually rather puny. It's only about 4 million times the mass of the sun. If you look at the Andromeda galaxy, which is our sort of sister galaxy or nearest big neighbor, its black hole is about 100 million times the mass of the sun. So it has a much bigger black hole. Good question, like why did that happen, right? We're relatively similar looking galaxies otherwise. Why did they get a black hole that's 25 times bigger than ours? Who knows, right? But this black hole also seems to do a lot of things to the galaxy, right? Now, black holes are not necessary for the formation of galaxies. In fact, if we look at we know of many galaxies that don't have black holes. They're generally quite small galaxies. So it's not that they're necessary, but nonetheless, when they do get fairly large, they seem to be part of the process that kills galaxies. And what do I mean by killing a galaxy? What I mean by killing a galaxy is that, of course, a galaxy is a collection of stars. So those stars had to form. So the galaxy was born. It accreted material from the intergalactic medium, got enough mass to start forming some stars. Those stars grew and grew and grew as more and more material fell in. But it turns out in the universe, all the really most massive galaxies are not forming stars anymore. And this is known since essentially the time of Hubble. Yet I would say at this point, more than 100 years later, why that is not terribly well understood. But the one thing that we have been able to connect it with is these central black holes. That once you have a sufficiently sizable central black hole, it seems that for some reason, that kills the galaxy. And that's just an empirical correlation from observations. Something like the Milky Way, which is a very small black hole, we're still forming stars, like we have over the last, essentially, roughly last 10 billion years. Andromeda, on the other hand, has a much larger black hole, still not that large, really, only 100 million, not tens of billions or anything. But nonetheless, you can definitely see that its rate of star formation has been curtailed, right? It doesn't form stars at the same rate as the Milky Way. In fact, it forms at about a quarter the rate of the Milky Way at most. So we're starting to see this process in Andromeda, but of course we can't wait around for billions of years to figure out where it's going to go. We have to sort of decipher what's going to go on by looking at a large sample of galaxies and try to connect the dots a little bit. And so why is it that we think that black holes kill galaxies? The basic answer is that black holes are incredibly efficient engines for converting mc squared into E, if you go back to Einstein's old famous equation.
So it all just ends up being broken down into the energy that made it.
Exactly, right? So as the black hole accretes material, because it's such a dense object and it has so much gravity, it can accelerate that stuff to incredible, close to the speed of light. And when it does that, objects tend to radiate, they radiate very efficiently, and eventually you can just convert about 10% of the accreted mass into energy. But remember that c squared, that's the speed of light squared. Speed of light is a very big number. You square it, that's a huge number. So even when you take a little bit of mass, as we know from atomic bombs, just a tiny bit of mass turns into a huge amount of energy. So now you imagine this black hole, if it gets big enough, right now that must mean that it's brought in all this mass. During that process where it brings in the mass, I like to say that black holes are very messy eaters, right? They have all this stuff around us. They only eat about 10% of it, and then 90% of it they throw out in incredibly high energies. So now you're adding all this incredible energy into the surrounding gas and into the surrounding galaxy, into the surrounding intergalactic medium. And what does that do? Well, what that does is it heats the gas up, right? It's like dumping a giant heater into the galaxy. And when it heats the gas up, it then prevents that gas from being able to settle down into the galaxy very nicely and form nice stars. So effectively, the way that black holes kill galaxies is to actually dump huge amounts of energy into the surrounding gas. And that's a process that we've actually been able to sort of observe, or at least observe some signs of it. But again, because it's occurring in the gas, it's not as easy to determine, it's not as easy to see directly as stars in galaxies. So we have to kind of infer things a little bit. And again, simulations play a really big role in that, because in the simulations, we can try to model this process directly. And that's some of the most recent work that we've been working on in our simulations, is trying to model that process as carefully and faithfully as we can, in order to understand how it is that the energy from these accreting black holes manages to eventually, over perhaps millions or hundreds of millions or billions of years, eventually just sort of starve a galaxy from gas and therefore kill it.
Okay, so I always thought that it gets sucked in and kind of chewed up and destroyed that way, but that's not right at all then.
Exactly. So it's in fact exactly the opposite, right? So you can think of it as creating a cocoon, which effectively lays the galaxy under siege. Like no material can now come into the galaxy because it's enveloped in this incredibly hot corona. And we see these hot coronae in X-ray emission. So we can go out with X-ray telescopes. The atmosphere is opaque to X-rays, but if we can put one in space, which we have, there was a new satellite, a new X-ray telescope launched fairly recently called eRosita, launched by the European Space Agency. And this is going to provide us with an unprecedented map of the X-ray sky. So we're going to see where this is happening, right? And we're going to be able to understand a little bit more about maybe how the black holes are heating the gas, how the black holes are keeping the gas hot and starving galaxies. So this is the kind of way in which the observations go in a new direction. The simulations go, oh, okay, let's think about what we can learn now if we had this great new X-ray telescope up there, right? So that's kind of how it goes.
Does that work by like sending out X-rays and then bouncing back for it to detect?
Well, it doesn't send anything out. It's passive, right? It just collects X-ray photons.
Oh, okay, so the X-rays are already there.
Yeah, so you just point it at a certain patch in the sky. The tricky part is that X-rays, well, they tend to go through things, right? As you know from going to the doctors, they go through your body certainly, and they certainly also go through the CCD in your camera, in your cell phone, for instance. You can't take a picture of an X-ray source with that. You need a special type of detector to capture X-rays. That's why you go to the doctor's office and they have those big machines. So now we have to put that whole contraption into space and trying to get extremely, extremely sensitive X-ray measurements. So it's a difficult problem. It's definitely a different sort of telescope than one that captures visible light or even infrared light. But luckily, we've been able to do it since the 1960s.
Compared to others that you use, then it's probably quite an old technology.
Yes, and the question is just getting bigger and better telescopes that are far more sensitive. So, I mean, the very first ones, couldn't basically detect anything, but it was nice to sort of see the concept. But yeah, so it's a long process, and astronomy is a very, I would say, technologically driven field. New advances are in large part driven by the ability of people to build better telescopes, build more sensitive detectors, build bigger computers that can do the analysis, run bigger simulations. And this just allows us to improve that level of detail and really test ideas much more carefully than we could when we had less good data, basically.
With the telescopes, can you actually see what a black hole is? Because I don't personally know what a black hole really is.
It's a good question. What is a black hole? And it's not entirely clear. There's the colloquial definition, which is not entirely accurate, but good enough usually, which is that even light cannot escape from a black hole. So as you know, things have an escape velocity. So for instance, from the surface of the Earth, you throw a ball up in the air, it'll fall back down. It won't escape the Earth, right? And in fact, you have to throw a ball very, very hard, or like SpaceX just did, launch a rocket, and that rocket has to achieve a so-called escape velocity. And from the surface of the Earth, that escape velocity is around 12 kilometers per second, which is pretty fast. So The idea is, of course, that the speed of light is very, very fast, but it's not infinite. So imagine that there was an object, you were standing on an object that was so dense and had so much gravity that even when you throw something at the speed of light, you had, the best arm in the world and you could throw something even at the speed of light, it would still not escape. It would still fall back, right? And that's a black hole. So this is, of course, pretty tricky because that means, well, this is why it's called a black hole, because it emits no light. No light can escape from it. So then the question is, well, how do we even see it? The idea is, of course, that stuff isn't getting out, but stuff is going in because of its large gravity. It's being attracted. And as I said, essentially that causes a lot of emission of high energy particles, things like that, things we can detect in the X-rays and even in the radio, as it turns out. But the point is that that black hole has effectively a surface. There's a distance at which effectively light can no longer escape. If it gets closer than that to a black hole. And that distance for a non-rotating black hole, just to be simple, is known as the Schwarzschild radius. And so if you were just looking out in space and a black hole happened to be next to you, let's just assume you weren't getting drawn in or anything, you magically could just sit there and look at the black hole. You would see all the stars and everything behind the black hole. Within the black hole, you'd see nothing. It would be black because any light that was behind the black hole would simply be falling into the black hole and would never get to you. But there is another way to detect black holes, and this is a fascinating thing that was first not discovered, but sort of hypothesized, I would say, by Albert Einstein in his theory of general relativity, which is that mass can bend light. So this is known as gravitational lensing. And so if there's stuff behind the black hole, the incredible density and mass of the black hole bends the path of light and focuses it effectively, just like a lens, in your eyeglasses focus light. It bends the light and focuses it into your telescope. And because of this, we can use gravitational lensing to try to detect where black holes are and what black holes are doing. So just recently, there was the first image of an actual black hole, right? And what do I mean by that? That means they actually imaged something effectively like the event horizon. This event horizon is at the Schwarzschild radius. And the way they did that is, just like with any sort of telescope or thing you're trying to look with, in order to resolve a very, very small, tiny thing like a black hole, you have to set your eyes, your effectively different telescope dishes very far apart, right? And so they effectively use the entire world. So they set up dishes all over the entire world, and they all look towards this particular nearby galaxy that has a very large black hole. And they were able to image not, of course, the black hole itself is black, but it has an accretion disk. It has material that is falling into that black hole. And the backside of that accretion disk is actually gravitationally lensed, right, in a way that creates a very unique pattern. And they were able to see the light coming not from within the black hole, light can't come from within the black hole, but from around the black hole at the accretion disk on the backside that was gravitationally lensed. They created incredibly sophisticated computer models to say, what would general relativity predict we would see given our telescope resolution? And in fact, this is exactly what they saw. So it was a stunning triumph of sort of technology of creating this worldwide network called the Event Horizon Telescope. It's not even actually an individual telescope; it's a whole bunch of them, and imaging this supermassive black hole, which is about, as it turns out, about 1 billion times the mass of the sun. So that's essentially our first direct image of a black hole, and you can see the hole in the center, the black region in the center, and you can see the accretion disk around it. You can see the gravitational lensing. It's very fuzzy. It's right at the limits of what we can do, but nonetheless, it was quite remarkable. So that's what a black hole looks like, really, to our telescopes.
But you don't really see it. You kind of see its effect.
Yeah, exactly. And so it's in a sense, it's only ever detected indirectly. There are different ways to detect black holes. So, for instance, the black hole in the center of our galaxy, how is that one detected? So in that case, it's extremely tricky because, as it turns out, our black hole in the center of our galaxy is not eating much right now. There isn't much of an accretion disk or anything around it. So there's nothing around it that's really shining particularly, right? Like with this other black hole, this much more massive one. There was no way to detect that directly. Instead, a few people, two separate groups actually, a group at the Max Planck Institute in Germany and a group at UCLA, University of California, Los Angeles, both came up with the idea and started saying, hey, listen, we can see stars around where we think the central black hole is. Why do we think that? Well, because what they've noticed is that as you look closer to this one spot in the galaxy, which happens to lie, right in the sort of the center region of what we can see of the Milky Way, the speed that these stars are moving around is getting faster and faster. Now, what does that mean? Well, you think about it, it's kind of like you've probably heard of a slingshot effect, right? Where if you send something very close to an object, as it gets really close in, or it's getting slung around the galaxy, and the velocity increases, right? So this is sort of a generic thing that, you get closer to the mass, you fall in, you move faster and faster. I mean, it's actually the same effect that, something falling on you from a large height ends up going very fast and hitting you in the head. And that's essentially the exact same thing. So the point is that they were seeing all these stars moving around at incredibly high velocities around this point that had nothing. Right? There was nothing at the center they could pinpoint based on the movement of all these different stars. It's like they all seem to be going around this one point, and yet there's nothing there, right? We can't see anything in the optical or in the infrared or anything like that. And they could estimate and say, how big a mass do you need in that little tiny region where these stars are all whizzing around in order for the stars to have the speeds that they do? And that answer was 4 million times the mass of the sun. So this is actually how the black hole in the center of the Milky Way was detected. It was essentially done, again, indirectly, by looking at the dynamical measurements of the stars orbiting very close to that black hole.
So at that point, it's just using maths to calculate it.
Exactly. Yeah, and they had to monitor these stars, even they're moving around very fast by astronomical scales, but of course this is all happening, it's about 25,000 light years away at the center of our galaxy. That's how far out the sun is from the center of the galaxy. We're kind of in the suburbs here. So it's very fast by astronomical standards, but they still had to monitor for a long time. So each one monitored for close to a decade. And then finally, both of them concluded that, yeah, this is what it had to be. It had to be a black hole. There was nothing else we knew of that could be that massive in such a small space. It would have to be a black hole.
I guess because there's no light coming back either.
Exactly, yeah. It's totally dark there. Now, it is the case that this Event Horizon Telescope is trying to do the same thing that they did with this other galaxy, and that galaxy turns out to be M87. It's a nearby elliptical galaxy. So they're trying to do the same thing with the black hole in the Milky Way. The good news is it's much closer than M87. The bad news is the black hole's a lot smaller, right? So you're kind of competing effects. And on top of which, unlike the black hole in M87, the black hole at the center of the Milky Way doesn't seem to be accreting much. But it looks like it is accreting something. So they're hopeful that they will be able to actually do a similar image with the Event Horizon Telescope of our own Milky Way black hole, which is called Sagittarius A star, is generally how the astronomy community refers to it. So we're hopeful in the next year or so this will be something that will happen.
Oh, that seems really soon. Technology moves pretty fast.
Exactly. It's really it's a phenomenal technological achievement what they did with the Event Horizon Telescope. And the idea is, of course, interferometry, which means sort of looking with multiple dishes spaced at large distances and then looking for the slight delay of one telescope versus the other. So as the light comes to us, there'll be a slight shift in where it's hitting the wave phase that's hitting the telescope of one dish versus another dish, very on another continent or something. And what was in fact a great limitation was our ability to measure and timestamp these photons accurately enough. So is it really a matter of like technologically developing better clocks, if you want to think about it that way? Unfortunately, they can't communicate instantaneously because they're so far away, but they can sort of timestamp the different wavefronts and then collect all the data. And thanks again to huge amounts of processing that's now available, thanks to Google and the World Wide Web and all these great computer advances. Now we have the technology to be able to actually combine all that data and analyze it and actually do some science with it. So this is just would not have been possible 10 years ago, for instance.
Yeah. And do black holes always exist in a galaxy, or do they take time to develop?
Yeah, so the smallest galaxies clearly do not have black holes. And so the thinking is that a black hole is basically something that forms a little bit later in a galaxy's existence. And if you think about it, it makes sense. You can think of a black hole as sort of a cosmic garbage dump, right? Gravity keeps attracting, everything goes to the middle. Eventually, the stuff just piles up and piles up and piles up, and it'll eventually become super dense and massive. And that's your supermassive black hole. Now, typically, you have to seed it. You have to get that process started. We do know how, for instance, that very massive stars that are much, much bigger than the sun, maybe 40 or 50 or 100 times bigger than the sun, they're very rare, but they do exist. And those stars, when they die, when they run out of hydrogen to keep burning, it is believed that those stars will, because they're so incredibly massive, they'll just directly collapse to a black hole. Now, those black holes will only have, 40 or 50 or 100 times the mass of the sun, minus whatever they threw off in the explosion associated with collapsing down, maybe a hypernova or something like this. So that's very small compared to the millions of solar masses, but that's how you start it off, right? So the idea is you start off with maybe having not just one of these, but a whole bunch of them collected together in the center of the galaxy. All these stars, they're very massive. They all go supernova or hypernova. They explode. They form into black holes. Those black holes eventually merge together, and suddenly you have a little starter, right? And as the black hole continues to grow in mass, it attracts faster and faster because it has more and more mass, and so it just keeps growing and growing and growing. So that's kind of how we think the whole process got going. But again, it takes a little bit of time for all this to happen. The galaxies, formed before this.
Do we know if it ever stops growing?
Yeah, good question. I think the answer is no, not technically, right? Black holes, there's no upper limit known on the mass of the black hole. But the thing is, they can pretty much effectively stop growing, right? And the problem is, just like a galaxy needs sort of gas and fuel to grow, black holes do too. And it's much more efficient to bring in something, I'm not using too big a word here, dissipative, right? Something that basically has friction. I guess that's the way to think about it. One way to think about it is imagine a big marble basin, right? Like our big steel basin that's completely frictionless. And you're rolling marbles around in this basin, right? And if it was completely frictionless, unless you aimed right at the drain, right? Unless it was, perfectly aimed, your little marble that you threw in will just keep going forever. It just keeps going back and forth in the big basin, zooming around, but it never gets down to the middle. Only if you have friction does it allow that marble to eventually sort of spiral down and go down and slow and slow and slower. It's losing energy as it does it. It has to lose energy. It has to give that energy to something, and that's friction. So gas has a lot of friction. So gas can really get down into the black hole much more easily than stars. Stars are like those little, mostly frictionless marbles just kind of whizzing through space, right? They're big. They don't suffer much friction at all. So this is why black holes prefer to eat gas. The problem is, of course, that for the same reason that these massive galaxies die out and stop forming stars is because they don't have gas anymore. Well, for the same reason, that black hole will stop growing too, because it also doesn't get gas. I mean, if the galaxy's not getting gas, how can the center of the galaxy get gas, right? So that just means that essentially black holes, in effect, kill themselves. By killing the galaxy that they live in, they eventually just commit suicide. So that's what we believe, stops black holes from just going infinitely big. But in principle, if there was a way to just continue to feed it gas, it would just keep growing and growing, and it will still grow. I mean, eventually stars do have a little bit of friction and stuff, so they do fall in and things like that. So it does grow, but much, much more slowly than early in its life when there was a lot of gas around for it to just have its little fun feasties.
Now that we're getting kind of closer to the end of this episode, I've got a few Mythbusters which I'm hoping you can answer, if that's okay.
Sure.
So the first one is, obviously we've all heard of the Big Bang, but is the Big Crunch real?
So no one can predict the future, for sure. However, all of our current models predict that there will never be a big crunch. It's not that it couldn't be possible, it could be. And the idea, again, it goes back to the same idea of escape velocity of throwing a ball in the air. The universe got effectively thrown into the air, if you want to think about it. That's really a kind of a poor analogy, really. And it started expanding with the Big Bang. So it had this very fast expansion rate. And there is, of course, mass in the universe, and that mass has gravity. And therefore, the universe is kind of attracting itself. So it's slowing its own expansion down, right? Effectively, like, the ball that gets thrown up slows down first. Now, that all made sense. Early in the universe, that's what it does. It turns out that about maybe 7 billion years ago, so roughly halfway through the universe's age, maybe about 5 billion years ago, the universe suddenly started accelerating its expansion, which was a very strange thing. And this was what was discovered in the 1990s. It's as strange as you throw a ball in the air. Initially, it starts to slow down, and then suddenly it just starts shooting off into the air. I mean, it's bizarre, right? And no one knows why this is exactly. We've assigned a name to this phenomenon called dark energy. Maybe you've heard of dark energy. It has very little to do with dark matter, by the way. It's just kind of a similar word. Yeah, so dark energy is the thing that is causing the universe to accelerate its expansion.
Right.
We don't know what it is. Interestingly, Einstein's theory of general relativity allows for a term that can be added in, sort of like a free constant that can be just thrown into the equation. Very interestingly about this, so that Einstein was around in in the early 1900s, and the expansion of the universe was not discovered by Hubble until the late 1920s. So Einstein didn't know the universe was expanding. He assumed, just like everyone, that the universe is just static, infinite. I mean, it's always been there. It's just what it is. When he wrote down his equation of general relativity, and he said, oh, why don't I apply my equation of general relativity to the whole universe? Well, he immediately realized exactly what I just described to you, that the universe shouldn't be static. If you started it off just at a standstill, it's like dropping a ball. It'll fall back in on itself. And so Einstein threw in this number, which he called a cosmological constant, which pushed out against this attraction and forced the universe to be static. And so he invented the cosmological constant. He didn't invent it. He just basically said, this number in my equations represents the thing that keeps the universe static. Because, of course, we all know the universe is static, right? So later on, of course, when Hubble came up with his discovery, Einstein, had the big facepalm moment and go, oh, geez. And so, he would later call this his greatest blunder, right? Because he basically was led by his own presuppositions rather than what the equations were telling him. But of course, if you think about what this cosmological constant is, it's sort of like a thing, it's a pressure, right? It's sort of like the thing, that is pushing outwards against gravity. And so this same cosmological constant can now be repurposed to explain why the universe is accelerating. So it might be that it is there, it turns out. It's just has a different value than what Einstein wanted, but it has a value that now, for some reason, has sort of taken over at late time, at sort of the last half of the universe's age, and is now driving this expansion. So going back to your original sort of mythbuster, right? If this is really true, that there is this cosmological constant, right? And all the observations so far seem to be completely consistent, sort of maddeningly consistent with this idea, that the universe will just continue to accelerate and accelerate. So obviously in that case, you'll never have a big crunch because, it'll just sort of keep going, right? So that is currently our best model of the universe. But again, until we have a better understanding of what this dark energy is, maybe it's not a cosmological constant. There's a lot of reasons that astronomers don't like the idea of a cosmological constant. So I think the jury's still out on that one. It's one of the big mysteries, I think, of the 21st century is going to be to understand what this cosmological constant is and whether it means something fundamental about the forces that we know of in the universe. It might be something extremely fundamental. Right?
Now, the second question I have is about wormholes. And I guess it's a simple question. Are wormholes actually real?
Well, this is a complicated question, right? The way that this wormhole idea started is the idea that you have this concept called space-time. It's not a thing, really. It's just sort of a representation of how things move in the universe. And gravity can be thought of as a warp in space-time. So, in the somewhat poor but often used rubber sheet analogy, if you put a big steel ball on a rubber sheet, it creates a depression that attracts other things around it. And so this rubber sheet is then the quote unquote space-time. But that's not actually the case. So this is what Einstein's theory of general relativity says, this conceptually. But of course, space-time is not actually a thing like a rubber sheet. It's just the way in which things move, right? The way in which things respond to motion. But the point is, if the space-time is warped in some higher dimension that we can't perceive, perhaps we can jump the bridge. Perhaps there's ways to actually go between one point in three-dimensional space and another point very far away in three-dimensional space that just happens to be warped in a way that is close in these higher dimensions, right? And this is the idea of a wormhole. And I don't think it's a crazy idea. What is completely science fiction about it is the idea that it can be used for actually crossing large distances of the universe very fast. Like you could jump into a wormhole and come out some other side. That's completely would violate many, many laws of physics. So that part is not possible. So, but the existence of an idea like a wormhole, I think that remains to be seen. I mean, Einstein actually predicted that black holes would exist, and he thought, this is such a crazy idea that it's never going to be actually seen, right? And here we are in 2020 or 2018 or whatever, and they've detected black holes. So, who knows? I mean, maybe another 100, 500 years, whatever, we'll actually be able to detect wormholes. But the idea of using them for transportation and taking large shortcuts across the universe, I think is pretty far-fetched.
Yeah, but if they do exist, definitely don't jump into one.
Yeah, if you find one.
Now, I'm out of questions that I want to ask you, but I want to thank you for coming on to talk to me about astronomy and answering the questions that I had.
All right, well, thank you very much, Jack.
And for anyone who wants to find out some more, have a look in the description. There'll be some useful links there for you. You can also subscribe to us with a variety of podcast providers, or go to us on Twitter and Facebook to find out more about the work that we're doing and new podcasts coming out.